Hi everyone. Today we're going to start with the nonlinear system that I finished with last time. I want to show you the trajectories with a numerical simulation. Then we're going to learn the Lotka-Volterra model, which appears in your exercise. And what? The whole exercise. Yeah. There was a message in the forum. And then I'm going to introduce the phenomenon of limit cycles, which is something we don't have in one-dimensional system and only in two-dimensional systems. I thought someone is missing, or maybe two people are missing. Right. Okay, so move to the black. I know that it's seen more clearly on the videos. So the system that we had was, where is it? Yes. And we saw that it has a fixed point at 1, 1. And we found that it was a saddle. And we had the two null lines. They were y equals 1/2 of x squared plus 1, and y equals x to the third. So a parabola and a cubic function. I need to turn on the projector now. Hope it won't take too much time to warm up. And what we did was draw the two null lines, and then they gave us basically the places where the trajectories must be horizontal or they must be vertical. And then knowing this and knowing the location and the type of the fixed point, we were able to try and complete the trajectories over the whole space. Sorry. Okay, so here we see the two null lines. Yeah. And the fixed point that we identified as a saddle. And here I have a simulation that allows me to choose different initial conditions, and it shows the trajectory from those initial conditions. So this is one trajectory, for example. This is the x dot equals 0 null line, and you see that the trajectory crosses it vertically. It has only a y component over there. Another trajectory. No. So I can start making trajectories, and you see that they all obey this. one trajectory from here. Here it crosses the y null line. The y dot equals 0 null line horizontally, as it should. Okay, now let's get closer to the fixed point. We see all the trajectories on this side of the plane, at least, running away from the fixed point. Let's pick something from within this area. So here they first go towards the fixed point, and then they go away from it. There. So you see the shape of the trajectories around the saddle. Of course, it will be very hard for me to pick a trajectory that will go into the saddle.
You can't because it's American direction.
You can zoom in.
Why do you think I can't?
You get
Because
a
it's
slight error and you get something
yeah,
outside.
exactly. Yeah, I can. Yeah.
No, you can zoom into the plane.
Yeah, let's zoom into the saddle. Like I said, I still probably won't be able to pick something that goes into the saddle. But it might be interesting to see more closely the behavior around the saddle. And notice that everything here crosses the null lines according to the rules that we have. Okay, so you see everything goes away from the saddle on this direction. And this is in line with the eigenvectors that I did not plot here, the eigenvectors. Let's see what the eigenvectors were. We had one vector was 1 and minus square root of 3. So if this would be 1, then minus the square root of 3 would be about here. And then 1 plus the square root of 3. So something like this. This is the eigenvector on which things go into the saddle, and this is the one on which they go out, the unstable manifold we talked about. This is the stable one. And notice how the stable manifold, it doesn't, of course, it doesn't necessarily follow this eigenvector direction. Here, it's pretty obvious that it cannot cross the null line here, right? Because it is itself a trajectory that goes into the fixed point, and a trajectory cannot cross the null line in such a way, right? So it must be curving somehow. Maybe here or something like that. Yeah, because everything that all the crossings of the null line must be horizontal. So even here, it must be horizontal. It must be to the right of the stable manifold. Okay, so this is a nice way of viewing the behavior in a two-dimensional system that's non-linear, and seeing how our guesses and our attempts at predicting the trajectories, they can actually be pretty good if we follow the rules of the crossings of the null line. We'll need a computer soon. Okay, So the reason that we need nonlinear system is that a lot of systems in nature are nonlinear, and what we had with the linear system, we had something like this, dy, y dot equals cx plus dy. This gave us a positive and negative feedback of the two variables on themselves and on each other, but it doesn't give us effects that are more complicated, like competition between the two variables. They can be two populations competing for food. There can be cooperation, for example, one gene aiding the expression of another gene. So we would like to be able to deal with terms like this, like square terms, terms like this, or just y over x, if x somehow attenuates y. And in the model that we will see now, the Logistic model, there is a nice example of competition between two variables. So this is a population model where x will represent rabbits and y will represent sheep.
And if you have, let's say, trigonometric functions, you will take it to the second order?
If I have, I'd like to have trigonometric functions, yeah, but
You have x dot equals sinus.
So
you will take it to the second order?
no, not necessarily. Not necessarily. I will just try to find a fixed point, and if I can find analytically a fixed point, I will do linearization around the fixed point. So the linearization would give me, the first derivative will also be a trigonometric function, but then I substitute the fixed point, and I get a number for the eigenvalues, finding eigenvalues and eigenvectors. But one of the examples today will be for a second order system and what we do with it. So we have rabbits and sheep, and they inhabit the same environment, and they compete for the same resources, which is grass, basically. And I write now the equations for both of them. So this is the equation for x, and you can see that this part of the equation is just a logistic growth equation. It's equivalent to writing 3x times 1 minus x over 3. So it's like a logistic equation with a rate of 3 and a carrying capacity of 3. Now, what we have here is the conflict that we have with the sheep. So when y is big, then we have this term that is actually minus 2xy that inhibits the growth of the rabbits, and also when the rabbits are big, this becomes big. When there are many rabbits.
Paul?
Yeah.
What is the minus 2y and
This thing or this? This?
which?
This is the effect of the sheep on the rate of growth of the rabbits.
Also, the rabbits on yourself.
Yeah, it also contains an effect of the rabbits on themselves. But the idea is that it scales with both of them. Okay. Okay. Now y dot equals y times 2 minus x minus y. So we immediately see that the sheep grow more slowly. Their capacity is basically smaller. We will have here, it's like 2y times 1 minus y over 2. so the capacity is smaller, and the way the rabbits affect them is not as strong as the sheep affects the rabbit. So one rabbit would disturb one sheep less than one sheep would disturb one rabbit. Okay, and of course, when we deal with these populations, we assume they are continuous variables, and they should be larger than 0 or 0. So you can imagine that our units are units of thousands of rabbits and sheep, or hundreds. So it's virtually continuous. Now, when we are given such a system, we can do several things. We can start from finding fixed points, and we can start from finding null lines. Now, I will start from the fixed point. So one fixed point is 0, 0. You see, it has both derivatives going to 0. And then if we want to take the other term to 0, that produces other fixed points, so we can demand 3 minus x minus 2y equals 0, and this will give us x equals 3 minus 2y, and from the other term, 2 minus x minus y equals 0, so x equals 2 minus y. Now we can have x non-zero and this 0, so x equals 3 minus 2y, and y equals 0, we have this thing equals 0. So we will have 0 and 3 minus 2 times 0, that's just 3. If we do another mixing with x equals 0 and this non-zero, so we will have 0, 2 minus 0 equals 2 minus y, so y equals 2. And then if these terms are the ones that take the equations to 0, then we will have to solve this. So 2 minus y equals 3 minus 2y, and 3y. Yeah, y equals 1. Oh yeah, y equals 1. So y equals 1, x equals 3 minus 2, so that's 1, 1. So we have 4 fixed points. Right. Let's draw them. There will be drawn them. Okay, let's make the drawings here. I'll write them down again. We have 3, 0, 0, 2, and 1, 1. Of course, I don't know yet the stabilities of these 6 points. Now, again, I can move on to finding null lines, or I can start already analyzing these 6 points. So we'll start with the Jacobian and the analysis of the 6 points. Okay. 2y. This is the Jacobian, and now we'd like to evaluate it at each fixed point. j at 0, 0 equals 3, 0, 0, 2. This is obvious. Okay, we have lambda 1 equals 3 with v1 equals 1, 0, and lambda 2 equals 2 with v2 equals 0, 1. So these are the directions, v1, v2. And if I want to start drawing the trajectory, I would compare the values of the two lambdas. So lambda 1 is bigger, and this means that the growth along v1 will be stronger from the beginning. Yeah, and this will give me yeah, such a trajectory. No, should be like this. Okay, so why is it? It's very confusing. I'm sorry. It's a little different from the considerations for the stable fixed point. So yeah, like I did before. This way.
No lambda 2 large.
Yeah. No.
What?
Large connection in V2.
Say again?
Shouldn't it be like
Yeah.
it was before?
Like it was just
No, before it should be below y equals x.
below y equals this. Yeah, because first I grow on this, and then I start growing on this.
Faster.
That's it. Sorry for this confusion. Okay, we can move on to the next point. Okay. Obviously, it's an unstable fixed point. You can also check whether it's a node or a or a spiral. Right.
Isn't it a node because it has
Because
eigenvalues?
because it has real eigenvalues. Sometimes the markers go dry. Okay, j at 0, 3 equals minus 3. Minus 1. Here it's less clear, but we can just do tau equals minus 4 and the determinant equals 3. And then do our plot.
And your fixed point is 3, 0?
3, 0
Not
and
0, 3?
should be
Say again?
should be
Fixed
3,
point is
0.
3,
In
0.
the matrix, in the original matrix, it should be the second column, first row, it should be minus 2x, not minus 2y. Yes, exactly.
Minus 2y.
It's supposed to be minus 2x.
The point is 3 zeros though, not 0, 3. Right?
Yes. 0. You're right. Okay. minus 4, delta equals 3.
X is 3 and Y is 0.
X is 3 and Y is 0.
Yeah, it should be minus 2y, right?
Here,
I think, I mean, that's how,
To Y or
so
Y.
Alex is right.
no, but why, it should be here, 3.
No, the derivative is okay,
Probably
but
minus
the
3.
Minus 2x.
So, yeah, so it's minus 3.
you just put
No, minus 3x.
This is okay. So
Y.
minus,
okay.
This is it.
Yeah, so it's minus 3. Yeah.
okay, so the original was correct. Right. This is unstable, right? Tau square minus 4 equals 4 times 4. This is larger than that, so the curve passes above our point, and it's a regular stable node. And we can check for the eigenvalues. Tau square root tau plus square root of tau square minus 4 delta over 2. Okay, and if you do the eigenvectors, you get v1 equals v1. So let's draw them here. V2 is just 1, 0, it's this direction. And V1 is minus 3, 1. This direction. And they both have negative eigenvalues. So first of all, along the x-axis, we have convergence into this fixed point, and it's safe enough to assume that it goes here. So now, lambda 1 is smaller, and lambda 2 is bigger. This is V2, this is V1. So, this means that first we will converge to the fixed point along V2 and only then along V1. It's again, it's a little confusing because they have this angle between them. But if I start from here, for example, then first I will have convergence along V2 and then along V1. Like this. So actually I will approach the fixed point tangent to the vector with the smaller eigenvalue, because I already made my approach along the other vector. Okay, so then we have J at 0, 2.
But this time you will cross it, right? Go the other way
Say
around.
again?
This time you will cross the fixed point. You will be in its place.
Where?
The fixed point.
Here?
You won't cross the fixed point, right?
Where? Here?
Yeah.
Yeah, you don't cross the fixed point. And you don't have oscillations in this case, because it's a regular. Okay, so again, tau equals minus 3 delta equals 2. Okay, this is tau squared over 4 equals 9 over 4. This is larger than delta. So this is a regular stable node, and our lambdas we have v1 is 1 minus 2, v2 is 0, 1. Again, both eigenvalues are negative, so this on the y-axis we have trajectories going into the fixed point, and also here we have trajectories going directly into the fixed point. And as we said, we'll approach a fixed point tangent to the vector with a smaller eigenvalue. So this is v1. Now, what we have remaining is j at 1, 1. This is cell, and we'd like to know where its eigenvectors are, so they'll be our stable and unstable manifolds. Okay, lambda equals minus 2 plus minus, here I have tau squared is 4, minus 4 delta. This will be 8. These are our lambdas. Lambda 1 equals minus 1 plus square root of 2. This is positive. Lambda 2 is negative. And then we have v1 okay, I wasn't so sure about these vectors. I'd like to substitute them. So j times v1 say -1 plus 2 plus square root of 2. And on the bottom row, -1 plus 1 square root of 2 over 2. Into is this correct? Does anyone follow? Okay. Do I'll solve the V1 and V2 again. So let's say V1 equals Rs equal minus.
And the Jacobian have a 0?
The Jacobian did not have a 0.
2 minus h times y plus.
This one?
No, there is a 2 factor missing on the y over there.
Minus
Ah,
2y?
yes.
Yes. Copy wrong from my notebook. Okay, over here. Minus 1 plus square root of 2 times r. Okay, so this goes away, right? So, r equals minus 2 over 2. Okay, and if I do it for minus r plus 2s equals minus 2. Okay. Minus square root of 2, 1. That's this. V1 and V2 is square root of 2, 1. V2. V1 has the positive eigenvalue, and V2 has the negative eigenvalue. So along V1, things will go away until they should, the trajectory should converge with this point V1, and the same along the other direction. And along this direction, things should go into the fixed point. Probably there is some line that connects, obviously there is for sure some line that connects these two fixed points, and we can try to speculate about what happens in between. Something like this. We don't this, we can use the note lines to help us. So I'll just draw this with the note line. Oh, and then there's another small thing, and then we go into it. Okay. The note lines that we have are x equals 0. This is x dot equals 0. So x equals 0 and x equals 3 minus 2y. Like I did over there. X equals 3 minus 2y. Y dot equals 0 gives us y equals 0 and x equals 2 minus y. So x equals 0 is the y-axis. Indeed, on this axis there should be no x component to the trajectory. So here we have an incline, but the trajectories also go on it. Y equals 0 is just the x-axis, so there is no y component for the trajectories here. Let's start with x equals 2 minus y. So this should be 2 minus y. We should start from here and go here. So my drawing was inaccurate. First, for this part, the crossing should always be horizontal here. So this gives us a kind of anchor for the trajectory going from this fixed point to this fixed point. It tells us they might be horizontal when they cross this line. Here, the eigenvector that I drew should actually be a little lower than this, and then things go into the fixed point, and everything like this in this area should cross horizontally and then go into the fixed point. X equals 3 minus 2y, which means it starts here, and the slope minus 2y, it means we will be at 1.5 here. Okay. So there should be on this there should be no x components. So trajectories should be sorry, I was drawing the wrong thing. This is actually y equals x over 2 minus y equals minus 2y. So 2y equals 3 minus x. Y equals 3 over 2 minus x over 2, and 3 over 2 minus x over 2. So the slope is 1/2, and we should go there. Okay, so all the crossings here are vertical, like we drew in the first place. And here, okay, these crossings should actually lie on the line here. Okay. We can draw it bigger, but for now, I won't draw everything bigger, just the main things. Here we go. 1, 2, 3. We have the stable fixed points here. We have the saddle here. We have the null line. So that was going from here to here, and one going from 2 minus y equals 2 minus x. And as for the trajectories, I'll draw the important ones. So we have trajectories going into this fixed point and crossing this null line. Here we have some trajectory connecting the unstable point in the saddle. Also here. Trajectories on the axis. Here we should cross this null line vertically and then approach tangent to that eigenvectors that we drew. And here cross this horizontally and then approach. There is something going like this, and something going like this.
We draw three different pathways and approach.
Say again?
It seems like from the same point you have many different
Where is this one?
trajectories from the origin.
From this? I have, yeah. I can have different trajectories going out of the origin. So if I am exactly at the origin, I will go nowhere. If I'm just next to it, then I will go to certain places based on.
But that is in the plane exactly where you are.
Yeah.
So there's no, I don't see a difference.
You don't see a difference?
In the way you draw it, no.
No, you can't see the difference in the way I draw it. But this is what I'm getting at now. You see that some of the trajectories go into this fixed point and some of them go into this fixed point. And so we have two sinks here in the system, and each one has a basin of attraction. So in our case, the basin of attraction of the first fixed point, of this fixed point here, is everything that is under the stable manifold. Right? All this part of the phase plane is composed of trajectories that go into this fixed point. And the other part is composed of trajectories that go here. This is the other basin of attraction. So this is a term you should know, basin of attraction.
What is the basin? Say it again, please.
The basin. So for a fixed point x star of t, it is the basin of attraction is all x such that It's the area composed of all the points in the phase plane that go into a certain
What
fixed point.
determines how did you determine the line?
How did I know? Just because I know there is a saddle here, and around the saddle we have a stable manifold that divides trajectories that go to its right from trajectories that go to its left.
So it's what the eigenvector of the
Close to the
of
fixed
the
point, it overlaps the eigenvector, the border. But farther away from the fixed point, it's not the eigenvector anymore. Okay, it will be the line connecting this to this. So here it is tangent to this point eigenvector, but here it will be tangent to this point eigenvector. They're not necessarily the same eigenvector.
what's the line?
It's a curve. Okay.
So there is only one base of attraction here, or two?
Here we have two.
Two sides, right?
We have one basin is this area that I marked in blue. It's the basin of this point. The other one is the white area here, and it goes into this fixed point.
So it's not only between y and x, but everything on the left also, it's also including the when x is negative, right?
Yeah, but it's not physical in our system.
So it's not counted. Okay.
Yeah.
So is
Yeah.
it possible to determine analytically to write what is
What is
function if we can write it?
I can think. No, I think at least here, no, it's not possible. But I'll think about it after we take a break and get back to you. The border between the basins is called the separatrix. This is the curve that he asked if I can find analytically.
What are the properties of the basis of attraction?
What I
It's
wrote.
only
It goes into some fixed point.
Okay.
Okay.
So there will be always only one fixed point in the basin of
In a
attraction.
basin of attraction.
Right.
Yeah.
There's no chance that there will be two.
Yeah, there should be only one fixed point. And then unstable points or saddles should lie on the separatrices. When you think, sometimes people talking about protein folding talk about energy wells. So this is similar. So the bottom of the well would be a fixed point, and the well would be a basin of attraction. And in between you'll have ridges that are, each one is a separator. Also,
so this model will have only rabbit horses.
yeah, good point. Yes, in this model, in the end, one of the species will win. Okay, but this depends on the parameters that we put into it, like the rate of growth of each species and the amount of competition that it poses for the others. This is not necessarily the case in such models. We can have some harmony between them. It's not actually harmony. They always compete, but it will be an equilibrium. Okay, let's take a break of 10 minutes and then go on to the limit calculus.
יש כבר מה קו שיוביל לנו 0,0 ונגיע ל-1,1.
לא תמיד.
הוא לא קו ישר.
איך נראה העקומה הזאת?
איך היא נראית?
או הקו, או יש גם עקומה שאמורה לתת מ-1,1 להגיע ל-0,0.
מ-0,0 ל-1,1 ורק כאן? צריך לבדוק מה האייגנווקטור שמצאנו ל-0,0.
אין לי פה
זה יוצא קודם ללכת בכיוון של ציר X ואז ללכת בכיוון של ציר Y.
כן?
יותר חזק בכיוון של ציר X.
לצאת מ-0,0 קרוב ל... ואז אתה צריך, בשלב מסוים אתה צריך להתאחד עם זה שכתבנו שהוא זה היה מינוס שורש, זה היה 1 ושורש 2. אז 1 ושורש 2,
אני לא יודעת, אני לא יודעת.
לא, שורש 2 1. נגיד שזה 1 וזה 1, שורש 2 1.
כן, שקוראים דברים בוואטי אותם. כן.
כאילו אתה צריך לעשות איזה פיתול.
אני יכול גם לעשות חץ על הקו הזה בכיוון השני. יצאתי 1-1 ואני הולך להגיע ל-0-0.
לא, כי 0-0 היא לא יחסית.
זה רק one way.
כן.
אני לא חושבת ששאול הבית, בכלליות, השאלה השנייה, הם מסתכלים C ו-D, רק פשוט לוודא שהבנתי נכון, אם פספסתי משהו, פשוט כאילו ציירתי את הממוצעים, ואז את הדינמיקות, וכאילו בכל אחת,
זה יותר גדול אבל, כי גם לי קשה לראות וגם לא שיהיה הרבה יותר קל, אם תעשית יותר גדול.
ואז בכלליות ציירתי כאילו את הכיוון הכללי, ונותר שואלים אם יש כאילו עוד משהו שכאילו צריך לעשות. כאילו ראשון לפירוט נורא ארוך. כלומר, כאילו, לעומת נגיד השעות הקודמות ששם פשוט היה צריך נגיד לצייר טראג'קטורי מסוים ולראות.
Representative trajectory. זה יותר representative trajectory, זה יותר מסלולים שהולכים במרחב.
פשוט לנחשב.
כן.
אוקיי. סתם אם תקרוא נקודות התחלה שונות ו... אוקיי. סתם, מה עשית בהתחלה?
כמו שעשיתי, את מנסה לייצג את מה שקורה במערכת באזורים השונים. אני צריכה שזה יהיה שיהיו לך מסלולים שעוברים לפחות לכל אזור, שיש פה איזה 4 אזורים בין המוצינות. אז זה קשה לי אזור שאני בכלל עושים את זה. ואת צריכה שהם תמיד יצייתו לכיוונים שציירת על המוצינות, וזה כבר גם למה שציירת פה בין המוצינות. אז בכל השטח הזה לא יכול להיות מסלול שיחסים עליו פונים שמאלה. או למעלה.
כן, פשוט לבחור כמה נקודות למסלולים.
כן.
אוקיי, ושאתה מתכוון את זה באחת ממילים, זה פשוט יותר כאילו...
כן, אז את יכולה להגיד, אם אנחנו מתחילים באזור הזה והזה, אז נגיע לתוך נקודת השם. או שנלך לכיוון אינסוף ושם.
בסדר, וקנה רציתי לבדק לגבי השאלה הראשונה, שפה כתקנה ציירתי את זה כזה דקטורי, אז אני גם צריך לצייר ממוצעים פה דברים כאלה, פשוט כאילו לצייר דקטורי ו...
כן, עשינו אז, יש לך איזושהי מטריצה, זה A, B, C, D, כפול RS שווה משהו מרוכב, שהוא RS, ואז נגיד נקרא לזה S פלוס GI, ואז יש לך כאילו AR ועוד BS שווה S פלוס GI אז BS שווה S מינוס A פלוס GI כפול R, ואז אתה יכול למצוא את הוקטורים, אבל אתה לא יכול לצייר אותם. איך? כן, אתה לא...
כן, אין לי ציר בדיוק, אין לי, אוקיי. אז אתה כן מצפה שנמצא את הפתרון, אבל לא לצייר אותם? נגיד פה נראה לי אחד.
כן,
אבל צריך לצייר פה איזה משהו, ואז אני לא יודעת איך לצייר את זה. הנה, אוקיי,
ואז חשבתי שאתה לא צריך לצייר את הוקטורים. אתה לא צריך לצייר את הוקטורים, אבל מה שכן, אתה צריך בצורה כאילו על ידי הצבא נגיד להבין מה הכיוון. אז נגיד אתה יכול, יש לך נגיד פיקס פוינט פה, ואז אתה מחליף את הנקודה הזאת ובודק מה X דוט או מה Y דוט. פשוט נציב את הנקודה S01 במערכת ולראות אם היא הולכת ימינה או שמאלה, וזה כבר יגיד ספירלה נגיד שמתכנסת, אז זה אומר שהיא הולכת ככה. אם זו ספירלה שיוצאת, אז זה אומר דווקא כאילו
אז כאילו צריך לצייר את הווקטורים בעצם?
לצייר את האייגנווקטור לא לצייר במקרה הזה, אבל את הפרוג'קטורי לצייר פשוט ספירלה עם הכיוון הזה.
וזה אני אמור לדעת?
עם הצבא. פשוט על ידי הצבא שנקודה.
ולבדוק מה Y.
כן. ואז אומרים לך, תשים לב שלכיוון הזה יש קשר למבנה של A. זה אחד, נגיד, ה-C, אתה יכול לצפות את הכיוון.
אוקיי.
אבל, כן, אז בוא נגיד שקיבלת משהו כזה, אז אתה יכול להציב R שווה 1, ואז אתה מיד מקבל את S.
מה?
את S. אם R שווה 1, אז זה S. והוא מרוכב.
הבנתי. אז נשאיר לך את הפתרונות מורכבים. לא לצייר את האייגנווקטור. אוקיי. טוב, זה פתר לי את הרמה. אוקיי, תודה.
צריך אותו.
אני חושב שאתה צריך אותו בשביל לעשות תיקון. So in this lesson, we'll get to know a phenomenon called limit cycles. And this is something that you can only get in two-dimensional system or in higher dimensional systems.
Bob, a question?
Yeah.
Last time we talked about what Lotka-Volterra model.
Yeah. Lotka-Volterra model.
Volterra.
Volterra. And it's a model of two competing populations. And like Hagai said, the outcome of our model was that in the end you can have only sheep or only rabbits. But other parameters can give you different results. Okay, so we'll see the limit cycles using just first an example. So we're looking at the system x dot equals x minus y minus x times x squared plus y squared. Y dot equals x plus y minus y times x squared plus y squared. This is our system. There is a fixed point here, 0, 0. This is the only fixed point in this case, but normally you would need to check somehow that there are no other fixed points. We can write the Jacobian of this system. So this is 1 minus x squared plus y squared minus 2x to the third in this position. And then here we have minus 1 minus 2xy. 1 minus 2xy.
Minus 2x squared, not to the third.
To the third.
Right.
2x.
Exactly.
Yeah, you must be right because we must lose one power, right?
Now you are doing limit cycles?
Excuse me? Limit cycles, yeah. Yes. So okay, and I want to take this as 0, 0. And then I get 1 minus 1, 1, 1. So tau equals 2. The determinant is also 2. We are somewhere around here. Tau squared over 4. So the curve, the parabola that distinguishes spirals from regular nodes passes under our point, and we have an unstable spiral. Okay, so this is about all we can do for this system. We can try to find the null lines, but it might be hard. And then I go to a numerical simulation in order to show you what happens here outside the region of the fixed point. Where do you prefer to have the plot? Up there or down here?
Down.
Down. Okay.
Maybe if you can take down the board.
But I want to draw on the plot. You may want to draw on it. Okay, so this is our unstable spiral, and I can start a trajectory. See, it spirals outwards from the fixed point. It seems to stop spiraling outwards to another one, also spiraling, converging into this cycle here. If I start from outside, then again, you don't see it, but it keeps revolving a little until it allows me to pick the next point. So everything here goes into this cycle, which is stable. And this is the fate of this system. It's doomed to eventually oscillate forever on this circle. Okay, and this is very interesting scientifically because it shows you that in a two-dimensional system, you can already have stable oscillations like you see sometimes in living cells, in heart cells, in pacemaker neurons. Sometimes you see this in mechanical systems. You have systems going into stable oscillations like bridges, and we don't want that to happen, or wings of airplanes that start to move. And also it appears in electrical circuits, for example. So it shows you that you only need, you remember in the one-dimensional system we could have no oscillations. It was either stable fixed point, unstable fixed point, but no oscillations like spirals around the fixed point. In the two-dimensional system, we got to know spirals. In the linear systems, we already saw all the types of fixed points, including closed orbits. So we had closed orbits there. And in the nonlinear system, we now get to know a new phenomenon, which is the limit cycle. So a limit cycle,
Can you show it analytically, or you just saying?
in this example, we can show it analytically, but usually no.
So what you do numeric integration, and you look at it, and you say, okay. So
Yeah, I'll tell you what you can do for limit cycles later on.
How do you find the direction of the...
How do you find the direction? Well, in your exercise, you were able to find the direction of the spiral based on say, the Jacobian at the fixed point. So if you know that these spirals evolve counterclockwise, then on the limit cycle it will also be
Can
counterclockwise.
we determine the direction of the spiral covariant with Wheelan?
It is in exercise 3.
And it's the same there?
It, it gives you a rule of thumb. Okay, it's not explained. But also you can substitute certain points and find direction. If you can find null lines, then it also will help you to determine the direction of the limit cycle.
And after you get into the circle, it's like the thing we saw, the orbit, closed
Like the
orbit?
closed orbit? Yes,
Same?
but not the same. I mean, on the limit cycle, it is okay. It's not the same because the definition of a limit cycle is an isolated uh, closed closed orbit. I wouldn't use an isolated closed trajectory. I wouldn't use the term orbit in order not to get confused.
What's the difference?
In a closed orbit, you could move a little outwards or inwards and find yourself on another closed orbit. So all the neighboring trajectories were also closed orbits. The limit cycle is isolated. The trajectories next to it are not themselves closed orbits, but they just lead into the limit cycle.
There's only one.
There's only one in this vicinity.
And the closed orbit is always a lot.
Yeah, a lot of them. Kind of like the continuum of fixed points on the line attractor.
So there is like a border to tell us if I start from this, I will go to this circle, and if I start on the other side, I'll go to the other circle.
Here you have only one circle.
No, in the case for you said
The closed orbit.
you said several things.
In the closed orbit.
Okay, yeah.
So in the closed orbit, there is no border. You move infinitesimally, and you find yourself in a different closed orbit with an infinitesimally smaller or larger amplitude. Okay?
I have another.
Yeah.
How can we know that we have a limit cycle?
Okay. So basically, you can't know. You can run simulations, and there are several methods of knowing that you don't have a limit cycle in the system. So you can rule out limit cycles. And there is maybe one method, and I think that we'll learn it unless we are really out of time. Not today, but in the next lesson. There is one method of narrowing in on the limit cycle and showing that it should exist in a certain region of space.
I think that in neural networks they use this term in neural networks.
Maybe.
They use limit cycle and they know that we have a limit cycle.
How did they know?
I don't know. They know many
No, it
things
was
that they don't know why.
Excuse me?
it was like Stochastic.
Okay.
Then it's like intuition. He didn't
Okay. Okay. So there is no analytical way of telling that you have a limit cycle except this method that we will learn, and that's not applicable in all cases. So, this is something that is okay. You can sometimes infer the existence of limit cycles. No definitive way. Okay, but you'll see in the next lesson. Okay, the limit cycle will always have a constant amplitude and a constant waveform and a constant period. Okay, it may not be.
Might have to be a circle.
It doesn't have to be a circle.
If you would have chosen not like a circle, it was maybe
Yeah.
also.
It could have been an elliptic one or something very irregular, like we'll see later on. But the idea is that the amplitude does not change, the waveform does not change, and the period stays the same. So you can have something very irregular, like, I don't know, maybe something like this, maybe on one of the axes, but it will stay the same forever and ever. Okay, not like a spiral where you might change the amplitude of your oscillation or the period.
I didn't understand. What did you put it down? The example what?
If you would plot x versus time or y versus time for generally for limit cycles, you might not get a sinusoidal function, but something irregular. Okay, maybe you might get something like this.
But it will be a periodic function.
It will be periodic, and the period will always stay constant on the limit cycle. And the amplitude will always be the same. Okay? Yeah.
Another question. This we can know, I guess, from the eigenvalues, we can know that we get a spiral, right?
A spiral.
So how? I mean, what change? How come it doesn't stay spiral? Because we are passing the fixed point.
Yes.
Or,
Mm-hmm. Okay. Other things that I should tell you about this. Okay. No, we move on to finding. Well, at least with this system, we can find analytically that there is a limit cycle. We don't need the projector anymore. So, in a few select systems like this one, you'll be able to find analytically that there is a limit cycle. And for this, it is useful to move to polar coordinates. So in the polar coordinates, we have r is the square root of x squared plus y squared, and theta is arctangent of y over x. Right? So if x and y are functions of time, we would like to know how r and theta depend on time. So we can do this. Okay, so r squared is x squared plus y squared. And now I would like to take the time derivative of this. So this will be 2r r dot equals 2x x dot plus 2y y dot.
This is just another example. Can you explain?
This is not an example. This is where I show how to convert this from the Cartesian coordinates into polar coordinates. Okay? I divide by 2r when I remember that r cannot equal 0 here, and r dot is x dot plus y dot divided by r. Here I just substituted for r, but it's not certain that we'll need it. So I got the dependence of r dot on x and x dot and y dot. So I will just plug in these expressions into this dependence that I found. Equals, first I have x times x minus y minus x times r squared. And then for y, I have y times x plus y minus y r squared all divided by r. So I have here 1 over r times x squared minus xy minus x squared r squared plus yx plus y squared minus y squared r squared. Sorry for blocking the view here. Okay, so xy cancels out. I have here 1 over r times x squared plus y squared minus r squared times x squared plus y squared. One minus r squared times x squared plus y squared. This is just r squared. And I'm left with r times 1 minus r squared. And now this is similar to the logistic relation, at least qualitatively. And I can draw r squared versus r and have such a function. And then I will have an unstable fixed point, a fixed point, and basically I'm done. So if I am able to transform my equation into polar coordinates, or conceivably maybe I will have to scale to stretch one of the dimensions like x or y. Yeah, I can use elliptic coordinate. It's the same, right? Scaling one of the dimensions. I can transform them to linear combinations where I will be able to do a polar coordinate. So if I am able to do some transformation and then get r dots versus r and see the fixed points here, I may be able to show analytically that there is a limit cycle.
Fixed point means
R does not change.
not change.
Yeah.
Cycling.
Yeah, so this is our spiral going out. This actually expresses the way our spiral goes out into the limit cycle, and this is from out of the limit cycle.
Where is there is no basin of attractions here?
Well, the whole plane is the basin of attraction of the limit cycle here.
What do you mean?
So everywhere on the xy plane, that's the basin of attraction.
Here.
Here, yeah. You see, there are no other stable fixed points. Or, yeah, this is a fixed point, but it represents a limit cycle. In general, there are unstable limit cycles or even half-stable limit cycles. So sometimes you would have a system with a stable limit cycle and then an unstable one and then a stable one, and then you'll have basins of attraction.
This is not always possible.
Yeah, this is usually not possible. Okay. But it shows you very nicely that why in this system there is a limit cycle. Now, if you do theta, so theta dot is basically you take the derivative of the arctangent. And you need to multiply by the internal derivative. Okay. So
Why is the minus sign? Part of the derivative of r times?
the minus sign,
Minus on the y
wait a minute, this is,
When you
when I take the,
multiply x,
maybe
no,
you get minus 1 over x squared. No,
yeah,
but it should be minus.
wait a minute. So if I take the internal derivative, this is y dot x minus x dot
just as
xy dot, right?
just
And then divided by x squared. Yeah, okay. No, I just wrote them in the reverse order. Yeah, okay. Okay. So this is right. This cancels out. Xy dot minus y x dot divided by 1 over y squared. Yeah, by x squared plus y squared. So this is in fact xy dot minus yx dot over r squared. And then we don't have time, but when you substitute these equations into this expression, you get that theta dot equals 1. This means that wherever you